Welcome to Chemical Process Safety. This video is about liquid pool evaporation. This is the situation in a chemical plant where maybe you've spilled some chemical and that is evaporating at a rate greater than what you would normally expect in a certain area of the chemical plant. I mean, this is important to make sure that your workers have not been overexposed or to make sure that your ventilation system is flushing the air appropriately. So the theory starts by considering principles of mass transfer. So Qm, the rate of evaporation, the mass rate of evaporation, is equal to the molecular weight of the toxicant times K, the mass transfer coefficient, times area, which is the area of the pool. So this is a side view, but this would be the area of the puddle or whatever that it is, times the quantity of the saturation pressure minus the partial pressure, all divided by R, the gas constant, times TL, the temperature of the liquid. And if you were talking about evaporation of water, for example, you can imagine that water will evaporate much slower in a humid room than it would in a very dry room. And that has to do with the difference between the partial pressure and the saturation pressure. Just to quickly review the concept here, partial pressure is the amount of the thing that's already in the vapor. And Psat, I like to think of, is the maximum saturation amount that the air can hold. So on a very humid day, for example, Pi, the partial pressure for water, would be very, very large. And on a very dry day, Pi would be small. The saturation pressure never changes, but it is a function of temperature. And that's why, for example, in the summertime, when it's very hot, it tends to be more humid because the saturation pressure is much greater. Now, if we're talking about toxicants, it's probably a fair assumption to assume that there's not a lot of toxicant in the air already. So Pi for many toxicants, that's the amount that's in there, is going to be very, very low. So this is either going to be negligible, meaning we can just cancel it out, or defined by the TLV. So if your ventilation system is designed to keep the concentration of a certain toxicant at or below the TLV level, the TLV is the greatest partial pressure that you could ever have. All right, so this is again a diagram from the side of what it might look like. And we'll assume that very close to the liquid gas interface, we have a local equilibrium. Obviously, we're probably never going to get to the situation where the entire room is in equilibrium because that would involve a lot of the toxicant evaporating, and that would be a very bad situation regardless. So we're just going to assume that very, very close to the spill, we've got equilibrium going on, and then further on beyond that, it's less than equilibrium. So just looking at a quick example for heptane, the concentration of saturation is 61,000 ppm, but the TLV is 400. So again, this is pointing out that Pi is usually much, much less than Pi sat. So we'll ignore that in our calculations. So here is what our calculation is. And here I have converted, I'm sorry, I've taken the ventilation equation and I've substituted this expression in for Qm. So in the ventilation, remember, it was Qm up in the top, but I've substituted all that and then I've canceled out R, for example. So in the derivation, one of the things you can do is assume that evaporation is slow. And if you do that, the temperature of the room or of the gas will be approximately equal to that of the liquid. And therefore, those terms can cancel. If the evaporation is faster, which typically it is not, then the temperature of the gas, which is T, is going to be different than the temperature of the liquid. But we'll assume that that is not the case. So we're down to this. So notice that this has two parameters, little k, which is the mixing coefficient, which we talked about in the ventilation video, and big K, which is the mass transfer coefficient. So little k, again, we've talked about before. You can see table 315 for that. If you're assuming well mixed, which is probably a bad assumption in chemical process safety, K would have a value of 1. Or if you're assuming less than ideal mixing, it would be somewhat less than that. So let's skip ahead to big K, the mass transfer coefficient. And recall from transport that K uses the kinetic theory of gases. So K is equal to A, which is just some parameter or some constant, times D to the 2/3 power. And D is called the diffusion coefficient. This is a property of the species, the diffusion medium, and the conditions. So the way that we'll treat this is by relating the diffusion coefficient K to some reference K naught, which is a reference state. So K over K naught is equal to D over D naught to the 2/3 power. So all I've done here is I've replaced K and D with ratios K over K0 and D over D0. And you can substitute D over D0 is simply the inverse, is proportional to the inverse square root of the molecular weights. So therefore, I can substitute that, make that change, and then rearrange to find K. In this class, the reference state that we'll use only is going to be water, and the diffusion coefficient for water is 0.83 centimeters per second. So when you're using this formula, you would plug in that number. This is, again, the diffusion coefficient for water, and you would plug in 18 grams per mole for molecular weight of your reference, because that is the molecular weight for water. And that's really it. Once you have the diffusion coefficient, you can plug in that. You can plug in the area of the pool. You can plug in the saturation pressure, which is a function of temperature, which you can find, by the way, using your knowledge from material energy balances. That is Antoine's equation, is the way that we typically handled it back then. Divided by K, the mixing coefficient, divided by the ventilation rate, divided by the pressure, and then multiplied by 10 to the 6th if your QM is in grams per meter cubed. All right, that's it for this video. See you next time.